So now, if you give me just a few moments to load up our project, because I'm assuming that's what we're going to be spending our time on. I can go hunting for some files. It's this one. I'll get my solutions out, so I have them handy as well. Why have I got two of them? Oh, that's because I went and changed some things that people mentioned to me. There we go. And that goes there. Okay, we're going first. Can I ask your permission? Any of the questions? This video is going to be split into two parts. The first part is just the lesson that we've just finished, right? The divergence theorem. The second part is help on the test, help on the project, right? And is it okay that if I put that online as well for the people who might want to have a look at it, including yourself, if you want to go back and say, what did you say again? Are we okay with that? And if any, and you're totally entitled to. We good? Right. If you're not happy with it, you tell me now, and that's fine. We'll still do the lesson. I just won't. I won't use you in the answer. Okay, I'm getting thumbs up. Jamie, I don't know about you. Did you say yes?
Yeah, straight.
We're good. Right. John had a good suggestion. I think I'll do that. I'm just going to say, is there any problems with question one? And you're going to say to me, nah, right? So, or you're just not going to say anything, right? And then I'll say question 5, and one of you is going to say, can we do question 5? And I'll go through it, right? So, is there anybody want one? Anybody got an issue with question 2? Do some of you need some time to just go hunting through your stuff to find out which number you had trouble with, or you got it in front of you? Are you good?
I know which one it is. It's just a ways down the line.
Right. Well, we'll definitely get to it. How about 3? Any issues with 3?
So I had a question on 3. We're just looking for the gradient, right? Not the
Yes.
directional driven.
Oh, we are looking for the. Well, are we? Well, the way I'm reading it, it says I'm asking for the gradient, but I did want the directional derivative. I just didn't phrase it in a way that I wanted it to be.
You're not
So
getting it.
I'm not getting it. Okay. If you did the gradient, let me jump to the screens so we can jump. The gradient part we'll assume you've done, but you can check it as we go through it. In that question, this is question 3. The gradient of the function ended up being 1, 1, 4. Right? I think that's what you should have got. At least, that's what I've got. Now, the vector that you're dealing with, which is this guy here, has to be a unit vector. So I'm going to move this over a little bit. Has to be a unit vector. So if you find the magnitude of it, I believe it becomes a nice number, 13. And so I know it says U, but it's really, it's not a unit vector. So it is now. And if you want to get the directional derivative guy, that fella, simply you take the gradient, which is this guy, and you do a dot product with the unit vector. So it's going to be 1, 1, 4, and a dot product with this fella, and this fella, and this fella. And eventually it ends up being that. So got a lot of corners, but you can probably fill in the, the dot product and the adding. Okay. Moving on then. Any issues with 4? Anybody want anything with 4? Anybody get an issue with either A or B in 5?
I asked you that and you told me that was a bad question.
Oh God, yes, I did. I'm telling you all now, and I thought I'd fixed that. In fact, I did. If you go into Canvas, you'll probably find it says, do not do this question. Right,
Okay.
so the good news is I'll just give you some points for it, since some of you were put through hell trying to figure out how to do it or look up how to do it. It is possible to do it, we just didn't cover the normal plane, and that was my fault. I thought we had. Okay, so 5, don't worry about. You can leave it blank or put in an attempt. You'll still get the points for it either way. So well, the good news is that you're guaranteed 4%. That one's a freebie. Right. We're now on to question 6. Do we have any issues with question 6? Okay. Do we have any issues with question 7? Okay. Do we have any issues with A or B from question 8? Okay. Do we have any issues, any questions about number 9? It looks like it's going to be the second half that's causing all the trouble now. Do we have any issues with question 10? How about 11 then?
Yeah, you can go over that one if you want, please.
Sure, no problem. You got to remember that you're answering problems for people who are not here as well, so it's okay to do that. Now, this question here, we're given an integral that looks like this guy, except there is no function, because all we're being asked to do is change the order of integration. That does not mean you just pick these guys up and switch them. In fact, that would be the worst thing you could do, because if you did that, you would be doing this fella. And aren't we breaking a very important rule, which is you cannot integrate the last thing with a variable in it, because that would mean your answer will have a variable in it. So we know that's not what to do. What we are, however, going to do is figure out what region in 2D space does that look like, draw a picture of it, and then change the order that we design it. Because right now we're designing as this is what X's does and this is what Y does. So let's look at this guy. X equals the square root of 1 minus y squared. If you square both sides and then you add a y squared to both sides, do you now see that what you had was a circle? And so I'll start off with a complete circle and then see what happened to it. Oh, but then the whole circle wasn't right, everything. Don't you only have x equals 0, right? X equals 0 to that circle. So what's going to happen here is that you can only pick values of x that are positive, because 0 is the lowest and then it goes bigger. So that means right now, that looks like what my shape is. If that was the only thing I told you, that would be your best guess at the shape. Now we bring in the y values. Oh, and the y values say, oh, wait a minute, you can't use all the possible y values because I'm only going to start at 0 and finish at 1. So if you do that, you end up with only this piece being valid. So what we figured out was that the combination of these two gives you a quarter of a circle in the first quadrant. And they built this shape doing the vertical scan, right? Well, actually, they did it doing the horizontal scan. They went that way. So let's switch. Let's do it vertically. Well, if you do vertical, what x starts at 0 and finishes at 1, and y starts at 0 and finishes here. Well, the equation of this curve is x squared plus y squared equals 1. If I want to find out what the equation of this curve is in terms of y equals, it ends up being that guy. So after all that work, you are now going to do numbers on the outside, x equals 0 to 1, y 0 to the square root of 1 minus x squared. And that guy doesn't change because we don't know who he is anyway. And this guy goes dy dx instead of dx dy. And that's what it was about.
Thank you.
Any questions with that? That makes sense. Right. Well, we're now on to, does anybody have an issue with question 12? Does 12 have any problems? Okay, so Teresa, Jeanette, no, I am putting you in the spot, but just a little bit of a spot. You do have a question that you have a problem with, or you just want to watch other people and make sure everyone's what you thought it was?
I do have a
Both.
question.
I have. Oh, sorry. Who are you talking to? It sounded like you said my
Ja-
name, but it might have been
I
yours.
said both of you, so Jeanette, you can answer first, then I'll ask Teresa. Jeanette, do you have a question? I don't need to know what it is yet, but do you have one, right?
Yeah, I have one question,
You
but
can
it's
have
like,
10. It's fine.
yeah.
What is, well, maybe you should continue that sentence. What about it's like?
Well, it's
Is
about
it-
number 22.
Okay, so
Yeah.
it's just a number. Right, Teresa, you here for the same reason? You got at least one guy?
Yep, I got 22 and then 17 and 19.
Okay, so we're coming towards the ones that everybody's having issues with, right? Because I was just getting a little bit worried that we're halfway through and we've only had a couple of questions, but in a way, I shouldn't be worried. That's a good sign, isn't it? It means you're pretty comfortable with it. Right, so we're now on to question 13. Does anybody have an issue with 13? Okay, some of these I did video in Canvas, so if you go there, you'll find it. We're on to 15 now. 15 had a change, and the change was that it should be 4 sine 2x. And I think someone did 4 sine squared x, and that's fine. She's going to keep that. But the one I changed it to was sine 2x, which is much easier. So is there any question with it, problem with 15? If you change the sine of x squared to the sine of 2x. Okay. So question 16. Any issues with that one? Right, I'm pretty sure I heard someone say 17. Do we have a problem with 17?
Yes, please.
Okay, let's get this guy going. We're given an integral, a triple integral to do. It's z equals -1 to 1. And there was a change to make it more realistic, and it was just to change the y's to -1 and 1. And then the x's are 0 to the square root of 1 minus y squared. And the function is 1 over 1 plus x squared plus y squared, all squared. And it's a dx, it's a dy, and it's a dz. And we're being asked to evaluate this integral and using cylindrical coordinates. So before we even start doing too much with that, the first thing I'm going to do is find out what this region looks like, at least the XY parts of it. The Z's are easy. What does this region look like picture-wise, right? So if I take x equals 0 and x equals the square root of 1 minus y squared, almost identical to the question we did a few minutes ago, this guy becomes x squared plus y squared equals 1. And this guy is 0. So that means you got this guy, right? X has to be 0 or the curve, right? Because that's a whole circle. And we're just saying that when you tell me X equals 0 is the small guy, it means this fill. Now, the Y goes from -1 to 1 means that that's actually the guy that we've got. Right, see the one we did a few minutes ago, wasn't it just the top piece? But this time it's -1 to 1, which means Y goes from here to here. And we are now looking at a region that can turn into polar. The radius of this circle, if you did a complete circle, would be 1. So there's the limits of integration of R. Theta is a bit of a pain. Right, you normally would do a curve starting at theta 0 and curving this way. But in this question, you have to start down here and then curve to there. The result is that this angle down here is -pi/2, and then you get to 0, and then you finish at vertical, which is +pi/2. Are you comfortable about that?
Yeah.
Yeah, I do actually recall that happened once in one of the questions in the last 10 weeks. So, if not that, something very similar to that. Right, so that is good. And for completeness sake, I'm just going to put Z in, because when you do cylindrical, Z's still Z, right? It never changes. So that's. Now, I'm going to do Z equals -1 to Z equals 1. And these two guys are now going to become, well, who cares? Theta from -pi/2 to theta equals +pi/2, and R goes from 0 to 1. And since everybody's a number, I can be quite flexible, can't I, about who's first, who's second. Now, I said 1 there, right? Because of this. Are we good? Right, now, this horrible mess has to be converted into R's or thetas, probably R's. Isn't that guy R squared? So you've got 1 plus R squared squared. Now the dxyz guy becomes R, dr, d theta, and finishing with a dz. Are we all comfortable about the finish to this then? 1 plus R squared, all squared, and this guy. And I'm coming to the place where I'm probably going to finish this one. This thing is variable separable. That guy and these two guys. This is going to be 1 dz, this is going to be 1 d theta. This guy is the only guy that really involves any work. Can you tell me what process you use to integrate an, oops, I've got my square, to integrate an R over 1 plus R squared squared? What process do you do for that one?
U sub.
And the U sub will be 1 plus R squared, and off you go and do your thing. And if you get it right, the answer will be pi/2. But there's a fair amount of math to prove that, right? So you can't just write pi/2 and expect to get points, okay? We good?
Got it. Yes, thank you very much.
Okay. $18. Did we have any issues with 18? It's absolutely horrible. According to my notes here, it finishes or ends up with, whatever you want to call it, 28/3 pi. Hopefully I did that right. Okay, what about 19?
Yes, please.
Okay. John, are your numbers getting picked up by other people now?
Yes, so far.
Right, so far, so there's 19 is let me, quickest way for me to do this is to show you the solution I've got and just talk through it, because I think there's so much going on. I'd be spending a lot of time just writing and talking, and you can, right, where the heck are we? Are you looking at the solution here? You're looking at a bubble on a bubble.
Yes.
Okay, so essentially what we've got is a big, I don't know what that color is, greenish yellow sphere, right? And we got a hemisphere, which is the blue guy. And we're being asked to find the volumes of solid bounded by them. So it's basically, you've got a solid at the top and you've got another solid at the bottom. So if, you can't really see it well, but if you can imagine in the overlap between those two, there's a kind of egg-shaped shape, right? Where the sphere and the other guy intersect. And if you rubbed out all that yellow stuff at the top and the excess stuff at the bottom, what you would see would be basically an egg. And we're trying to find the volume of that. So it's definitely going to be spherical coordinate system. And they tell us 2 cosine phi, and the other guy is rho equals 1, and the z equals 0 just tells you everything is above the xy plane. So I zoom in and make this bigger. That would be helpful. Okay. Let's do the coordinate system of the 2 pieces that they've got. This piece here, right? And then over here, we've got this other piece here. So essentially the shape's been broken into 2 parts. If you do rho equals 1, what you're getting is this guy. And if you do rho equals 2 cosine theta, rho goes from 0 to 2 cosine theta, right? So what are the limits of integration? Where are they coming from? In both of these questions, if you projected them onto the floor, you would see a circle. And so theta goes from 0 to 2 pi. And in this one, you get a circle of radius 1, so 0 goes to 1. And I'll talk about that middle one in a minute. In the other piece, you get a circle 0 to pi. In the other piece, you get 0 to 2 cosine pi, which is that guy. Actually, this here, I have just noticed. Yeah, it's okay. I fixed it later. Right, so the only thing we've got to figure out is what's happening in these 2 regions here. So it's a bit messy, but if you imagine a projection, a line out here, and you're trying to figure out what phi does, right? That point where my mouse is, right there, see that guy there? Right there. That's a very important point because it's where does this guy intersect with that guy? And so it's when is 2 cosine phi equal to 1? And 2 cosine phi is equal to 1 when cosine phi is a half, and that's where that pi upon 3 came from.
Did you
So
add the
it's-
row after the word hemisphere? Because mine doesn't have that row.
Okay, mine
What?
doesn't either.
Oh, sorry. Does that make this question easier?
Yes.
I don't know why mine. I guess this is my solution. So I guess maybe I forgot to type it in. Okay, so that rho equals 1 does make a big difference, right? Because 1 on its own doesn't make any sense.
No,
So,
it doesn't.
right, if you're thinking where the pi upon 3 came from, 0 to pi upon 3, because in this shape, you start vertical, which is phi equals 0, and then you curve down to, right, you rotate down to that intersection point. So this chunk here is basically giving you the top half of that egg shape. And then if you start off where this one finishes, which is pi upon 3, and then you finish on the floor, which is pi upon 2, and you use the formula rho is 2 cosine phi, right? Which is rho is 2 cosine phi. This piece here represents what would be the bottom of the egg shape. So 1 and the other guy. 0 to 2 pi for both of them. This one, the yellow guy, rho goes from 0 to pi upon 3. The blue half of the egg is pi upon 3 to pi upon 2. And once you've set this horrible mess up, the next 12 lines, probably is 12 lines, is really just integration. And in this case, they're variables separable. In this case, they're not. But as you fight your way through it, you will get 5/12 pi when you get to the end. So your goal is to find the integral of 0 to 2 pi, 0 to pi upon 3, 0 of 1 of this expression, and then 0 to 2 pi, pi upon 3 to pi upon 2, rho equals 0 to rho equals 2 cosine theta of this guy. And when you combine the two, 5/12 pi. That is a cool question, but that is a killer of a question. And not telling you rho equals 1 wasn't very helpful. So the key is that line there. If you write that line down, everything from that point onwards is just boring integration, right? With rho, thetas, and phi's. How about 20? Oops, let's kick off that one. I can do it myself now. Do we have an issue with 20? Okay. Oh, 20 came out as 0, 0, 32 thirds, as far as I'm concerned. Did you get 0, 0, 32 thirds? That's what my notes are.
For what number?
For question 20.
Yeah, I did.
Okay, so we're cool. If somebody got the same number as me, then the chances are I didn't screw up, because it's, you know, it's easy to screw up. And I will know I've screwed up because when I check your answers, everybody else is going to say it's 5 and I thought it was 4. And so I go back and I double check my working, and if I'm right, that's fine. If I'm wrong, I'll change it. Right, 21 was the Jacobians. Did anybody have problems with calculating the 3 Jacobians? We must be getting dead close to yours, Jamie, because there's only a few questions left. So here goes. Did we have any issues with question 22?
Yes.
Okay, let's
Yeah.
do that one.
I have a feeling this one.
Mhm.
Yeah.
Okay, so question 22, we're being asked to do a double integral and a change of variables. So we're going to use Jacobians, obviously. And the region R is described as x plus y equals 1, x plus y equals 2, x plus 2y equals 1, and x plus 2y equals 2.
Thanks.
Right?
Wait, that's
So-
not what mine said.
What does yours say?
Mine
not what mine-
says x plus
You-
3y. That's so much easier.
Oh,
Yeah, mine too.
sorry.
Yeah. I ended up splitting it into 2 separate calc 2
Oh, you-
integrals that were super ugly.
Oh,
I-
I'm
I
sorry.
did too.
Oh. So now the question is good. I don't need to do it, right?
We'll still go through it, but
Yeah, okay.
it's
Let's
so
go through
much
it then.
easier.
Okay. So would you agree that your change of variables will be these two guys then?
Oh my gosh, that's so much easier.
Okay. So your Jacobian that we're going to do here is going to be UV over XY, which I know is the wrong way around, but we'll fix it because what we want is we want to know what this guy is, right? But sometimes the information is not in a form that makes that easy. So this is easy to do. Partial derivative with respect to x of u and partial derivative of x and y. With that one. So what do you get? You get a 1, you get a 1, you get a 1, you get a 2. 2 take away 1 is 1. Well, you can't get nicer than 1, right, for a Jacobian. And so what will this guy be? Technically, this guy is 1 over the guy that we've just got. But since he's 1, he's also 1. But can you imagine that was 4? This would be a quarter, right? Now, what are the limits of integration going to look like? Well, x plus y equals 1 transfers into u being 1, and x plus y equaling 2 tells me that u equals 2. And then the x plus 2y equals 1 tells me that v is 1. And x plus 2y equals 2 tells me that v is 2. And so my integral will now be from u equals 1 to u equals 2, v equals 1 to v equals 2. Convert this guy into u's and v's. Well, he's pretty easy, right? He's just x plus y. The Jacobian. Did I get the right way around? Times, well, in my case, dv du. Well, that guy is 1. So you're basically doing 1 to 2, 1 to 2, u, dv, du, which splits very nicely into a 1 to 2 du and a 1 to 2 dv. And that guy is a half u squared. And that guy's basically just 1, and that gets you 2, and that gets you 4, take away a half, so I believe you get, do you get 4? Yeah, you get 4, so that's 3 halves. Yeah, so that would be a half times 2 squared, take away 1/2 times 2. That would be 4 times 2 is 2, take away a half times 2. That's 3 halves times 2. Anything else? Oh, it's not times 2. That guy's times 1. Excellent. The answer is 3 halves. Let me check. It is 3 halves. We are good to go. You feel much better now about the fact that it was just a, I don't know. I should be more careful about making sure that my questions match my solutions. Or at least the questions mark the solutions to the questions I made. Because I'm sure it's just a typo when you're typing things in or you copy and paste. I sometimes forget and I make a mistake. But at least it was a nicer answer because of the mistake, right?
Much nicer.
Okay. Do we have an issue with question 22?
Yeah, the second 22.
The second 22, yes.
Yeah. Could you
We do.
please?
Right. So there might be a notation, this squiggly thing, right? A lot of these questions I just get out of textbooks. And the reason I do that is because I know if I do a textbook, there is a pretty good chance that the answer is going to be pretty. Unfortunately, sometimes our notation doesn't quite match what we're used to. So I want you to just basically realize that this guy is the same thing as that. Right. So if you could figure that out, I think you'd be fine. So partial derivative x, partial derivative y, partial derivative of z, right? And so we are going to find essentially, eventually anyway, the little function guy that goes on here. So what do you have? Well, if you do a derivative of this guy with respect to x, you will get a cosine of xy plus z times the derivative of the inside function with respect to x. So I get that guy. If you do the middle one, you're going to get, with respect to y, you're going to get the cosine of xy. Let me check, yeah, xy plus z times the derivative of the inside with respect to y, which gives me an x. And if I'd planned ahead, I would have given myself more room. And if you do this one, you just get a cosine of xy plus z. Right. So that would be f x, f y, f z. Right? And that's pretty much the answer. That's all.
Oh, okay.
They only want the gradient, right?
Yeah, we would always do the,
Find the little baby F guy. Yeah.
find the
Um,
potential equation.
That's it. Since it never asked for it, you don't need to, but if you wanted to do it, it would probably be a lot of work. And secondly, I'm not sure that that's a conservative field, in which case it might not even be possible.
Yeah, I thought it was maybe a trick question, so I was trying to verify that it was a conservative field, and
And was it? Did it?
it
I
was
don't know.
really ugly. I couldn't even finish
You can
it.
do it, right? So chances are it wasn't then. Okay, we are on to question 23 then. Question 23, so if we haven't seen it, is a line integral of this guy passing through the point 0, 2 to the point 4, 8. And can we jump to the fact that the equation of the line joining these 2 points is 3 upon 2x add 2? Be comfortable with that. I never screwed up there. Did you get that, Teresa, when you did that?
Well, I did starting at point P, ending at Q, and I came up with
Okay.
line Q.
Okay, so if you did the vector joining P to Q, you would be doing 4 take away 0, 8 take away 2, and you would be coming up with what, 4 and 6, essentially. Is that the way
Yeah.
you went? Right.
Yeah.
It's equivalent, but the math will look a little bit different towards the end. That's the only difference. So, so can we stick to this one only because it's essentially the same as the one before rather than a
Mhm.
different approach? Right. If you look at this line, but you start here and you finish here, it's called a line segment. And you make x equals t in any of these situations. And then you make the y 3 upon 2t add 2. And what that will give you is a space curve. Because for these questions, you have to kind of turn the thing into like vector notation, a space curve, right? So you get this guy, t and then y in terms of t. You also get the t values of, to get this guy, make t or x 0, and to do this one, make the x 4 or the t 4. So this time I'm going to make sure I remember to use 0 and 4. What you then do is you differentiate this guy and you get the 1 and the 3 over 2. You then find the magnitude of this vector. And this ends up being 1 squared plus 3 upon 2 squared, which is 1 plus 9 quarters, which is 13 quarters, which is where that 13 over 2 came from. Are we good up to here?
Okay. Yep.
Right. So what we're now going to do is take the original line integral that uses x's and y's and convert it into a single integral using t. And the t is going to go from the start of the line to the t value that is the finish of the line. That's where I went wrong last time. The x squared, right? The x squared is going to be replaced by t, so it's t squared. And the y squared is going to be replaced by 3 upon 2t add 2 squared. And then you multiply by the magnitude of the derivative dt. And that's basically the formula that converts a line integral into parametric t's, right? It's that guy there. That's 0 and that's 4. This guy is t squared. Square that guy, you get 9 quarter t squared. That times that gets you 3. Eventually you'll get 6t add 4. The magnitude of the line segment is root 13 over 2 dt. And I'm going to pull out the root 13 over 2. And I'm going to combine this guy and get 13 quarters t squared plus 6t plus a 4 dt. This basically is just a good old-fashioned Calc 2 integral, which I'm going to actually start over here because I know I need a lot of room. And it's going to be add 1 to the power and divide by the new power. It's going to be 3 t squareds, and it's going to be a 4 t. And it's going to be evaluated at 0 and at 4. So that's going to be root 13 over 2, 13 twelfths 4 cubed, plus 3 times 4 squared, plus 4 times 4. Take away a lot of nothings. And I do not have my calculator with me, so I need some help here.
Okay.
This horrible mess will be some kind of fraction, either over 12 or it might be over 6, but I know it's going to be over something. So could someone do this for me and tell me what they got? Well, if you all wait for each other, we'll never get this done. So hopefully one of you is hitting buttons on the calculator. It'd be nice if 2 of you do it and we agree on the answer. That way, it's a good sign. But what do you get? It might be 6, it might be thirds, who knows? I'm just guessing it's 12ths.
I put something
Teresa,
in
you
wrong.
got some?
No, I think I put something in wrong. It came out to be kind of a goofy number.
I know it's late. It's hard to do things right when you're tired. I could try and do some of it. I mean, that's 48, I tell you that. And that bit's 16, and that bit's 64, and they're 13
First-
over 12.
For the first one, I got 208 over 3.
Okay. 2 over 8 over 3.
400
Anybody
over-
else? What? Say again?
Ends up being 400 over 3 and then times root 13 over 2. It gave me a decimal.
Yeah, but you can hit the math button and convert that into a fraction. But I don't get that answer. Well, I might. I could try it. What would that get? 1364, 13. That's the same as 640 plus 180 plus 192. That's 832, I hope, over 12. 832 over 12. 832 over 12. 832 does simplify. 832 over 12 simplifies as well. You can divide by 4. Can you divide by 4? Oh, you can. So that guy is 208 over 3. And then what, you add 48 and add 16 to that. Well, 48 is 120, 144 thirds. 16 is 48 thirds. Yikes. Okay. 352. 400.
I got 400 thirds.
Perfect. Square root of 13 over 2 times 400 thirds cancels down to 200 square root of 13 thirds, because the 2 cancels into the 400, which is the answer I gave you the first time we did that. 200 root 13 over 3. And that matches my my answer in my solution sheet. Yeah. Was it a bit cleaner the second time round?
Yes.
So
Thank
we
you.
were just, yeah, we were relying on this conversion that allows you to take x's and y's on a line curve and convert them into a single integral in t. And the trick is turn everybody into t's and find the magnitude of the derivative dt. That brings us to, is there a problem with the last question? Does anybody have an issue with question 24, which is really question 25?
If you could just set up 24.
Okay, so this guy here is really written down in a format that you probably don't recognize. So let me tell you who he is. He's that guy. And so we have a guy F, a two-dimensional vector field, which looks like that. And we have a curve y equals x squared, and it goes from the point 1, 1 to the point 3, 9. So if you sketch what that guy looks like, he starts here and he finishes here. There's 1, 1. There's 3, 9. And there's the curve. I'm going to find the parametric equation of that curve. It's very easy to do. It's almost the same as the last question. You make x equals t, and that makes y equals t squared. So my space curve that represents the curve that we have here is t followed by t squared. Its derivative is 1, 2t. We're good with that guy? What else do I need to do? In this case, this is a slightly different version because it's a dot product we're going to do. So let's move it over here. We are going to do the integral. Oh, I haven't done my start and finish value. 1, 1 has a t value of 1. 3, 9 has a t value of 3. So my t's are going to go from 1 to 3. The f guy is him. The second guy is the r dash guy, which is him, dt. So I'm basically doing f dot product r dash t dt. So I'm using that version now because of this being a two-dimensional vector instead of the previous one was just a single variable. You see, that's not a vector, that's just an expression. And this is a vector. And the only thing I need to do is replace the y in terms of t and the x's instead of t, dot product with the derivative vector dt. So that's a different, similar looking, but if you notice, it's not the magnitude of this dt, it's the vector r dash t with a dot product with f. So that guy times that guy gets me negative t squared. That guy times that guy gets me 2t squared. And now we have a nice good old fashioned single integral, which can be simplified. Power rule from 1 to 3. I may as well keep going. 3 cubed, 1 cubed, 26 thirds. So this guy here is just another version of that guy there. So actually, relatively clean question to